Now we're going to approximate the integral from 0 to 0.2 of x times the natural log of 1 plus x squared dx, correct to 6 decimal places. First, let's recall that we can express the natural log of 1 plus x as a power series. It is equal to the sum, as n goes from 1 to infinity, of negative 1 to the n minus 1 times x to the n over n. With that as our starting point, we can express x times the natural log of the quantity of 1 plus x squared as the sum as n goes from 1 to infinity of negative 1 to the n plus 1, x to the 2n plus 1 divided by n dx. Forgot the integral from 0 to 0.2. Let's talk a little bit about this. The 2n in the exponent comes from the fact that our base is 1 plus x squared and not 1 plus x. And the plus 1 comes from the extra factor of x that we see next to the natural log inside of the original integral. For this integration, we're going to use the power rule, as is the case with all power series. We have the sum as n goes from 1 to infinity of negative 1 to the n plus 1, x to the 2n plus 2, I forgot how to add 1 for a moment there, divided by, the n was already there, and then we have to divide by the new exponent, 2n plus 2. This is a definite integral, so we're going to evaluate from 0 to 0.2. Now, folks, I blew right past it, but this highlights one of the reasons that power series are so nice to work with, because calculus with them, differentiation, integration, it always involves the power rule. Here's what needs to happen now. We need to evaluate this sum with a bunch of terms, right? At 0 and 0.2, take the difference. We're still going to use the second fundamental theorem of calculus. So let's get this done. If n is equal to 1, now that's the starting point for our index, then we have negative 1 to the 1 plus 1, so a positive 1 there. And then if n is 1, we're going to have an exponent on x of 2n plus 2 is going to become 4, right? But we're going to evaluate this at 0.2. So we're going to end up with 0.2 to the fourth power in the numerator. In the denominator, now we have n times the quantity of 2n plus 2. If n is 1, that denominator is going to be 1 times 4. When n is 2, we have negative 1 to the 2 plus 1, so that's odd. We have a minus term. And then if n is 2, then the exponent on x is going to turn into 6. So we're going to have 0.2 to the 6th power divided by 2 times 6. For the next term, n equals 3. Positive, these are alternating, right? 0.2 to the 8th divided by 3 times 8. I'm going to put plus dot dot dot, goes on forever, but we still have to subtract what happens when we put 0 in place of x, but when we do that, we get 0 for all of our terms. So we have a few terms that we wrote out when x is 0.2, and then we have just a 0 when x is 0. How many terms do we need, though? Well, folks, remember there's something called the alternating series estimation theorem, and it says that the remainder, or the error, is not bigger than the first neglected term. We want this accurate to 6 decimal places, which means that we want the error in magnitude to be less than 0.000001. As it turns out, 0.2 to the 8th power divided by 24, the third term that we wrote down, is approximately 1 times 10 to the negative 7. So it turns out we only need the first two terms. 0.2 to the 4th power divided by 4 minus 0.2 to the 6th power divided by 12. That in a calculator will give us a result of approximately 0.000395. I stopped this at the 6th decimal place because I was asked for accurate up to 6 decimal places.